Hi guys, welcome to JIK 224 E-Kuliah series. I'm Dr. Sumian Sabah. This is the 5th video covering chapter 2, which is chirality centers. How are you going to determine chirality center? And so we will discuss more detail in this video. So upon completion of this topic, you should be able to identify chiral carbon atoms and other stereocenters. So here we have a chiral carbon. So the most common feature that leads to chirality in organic compound is the presence of chiral carbon. So a chiral carbon is a carbon atom bonded to 4 different groups. So here we have 1, 2, 3, 4 different groups that is located here in different colors. So the different colors indicate 4 different groups. And this chiral carbon is also known as asymmetric carbon atom, and it is often designated by asterisk or a star. Okay, so any chiral carbon, you have to label them as a star. What is stereocenter? A chiral carbon atom is the most common example of a chirality center. Chirality center belong to an even broader group called stereocenters. A stereocenter or a stereogenic atom is any atom at which the interchange of 2 groups give a stereoisomer. A chiral carbon and the double bonded carbon atom in cis-trans isomer are the most common types of stereocenter. So let's look more detail on this. So here we have a asymmetric carbon or chiral carbon attached to 4 different groups. This chiral carbon is an example of chirality center. Chirality center can be any atom other than carbon. So here we have an example of nitrogen that is attached to 4 different groups. And a chirality center is an example of stereocenter. So here we have a carbon atom in a double bond. So this is a stereocenter. This carbon is a stereocenter, but it is not a chiral carbon. Okay, this double bond carbon is not a chiral carbon. So later we will discuss more detail on this. So chiral carbon atoms are example of chirality center, which are example of stereocenters. In general, when you have no stereocenter, usually the molecule is achiral. When you have one stereocenter, it is always chiral. When you have 2 or more stereocenter, it may or may not be a chiral. To locate a stereocenter, you have to examine each tetrahedral carbon atom in a molecule and look at the 4 groups, not the 4 atoms bonded to it. Okay, so the first thing that you have to see is that the chirality center must be in tetrahedral shape. Okay, always omit from consideration all carbon atoms that cannot be tetrahedral stereogenic center. This includes CH2 and CH3 groups, any sp or sp2 hybridized carbon. So sp is when you have a triple bond and sp2 is when you have a double bond. So to locate a stereocenter, and in this case we will focus more in determining the chiral carbon as the stereocenter. Okay, so it must be in tetrahedral shape, and then we must omit any double or triple bond. So for example, here we have the bromo, chlorofluoro, iodo, methane. Okay, so we have 4 different groups here. So this carbon is the stereogenic center. Okay, why? Because this carbon, this is the stereogenic center. But when we have this another example, which is 3-bromohexane, we have 6 carbon here. We can identify only the 3rd carbon as the stereogenic center. Okay, because this carbon is attached to hydrogen, bromine, ethyl group, and propyl groups. Okay, so these two groups are different because one is ethyl group and one is propyl groups. Okay, so it must be connected to 4 different groups and not 4 different atoms. What about if we have multiple stereocenter? So larger organic molecules can have 2, 3 or even hundreds of stereogenic center. Okay, for example, here we have propoxypene, okay, that have 2 stereogenic center here at this carbon. And then we have ephedrine, also have 2 stereogenic center. While for fructose, okay, which is a simple sugar, we have 3 stereocenter. Stereocenter also can be located on a ring. Okay, stereocenter may also occur at carbon atoms that are part of a ring. To find a stereocenter on ring carbons, always draw the ring as flat polygons and look for tetrahedral carbon that are bonded to 4 different groups. So, for example, here we have methyl cyclopentane. We have methyl group here and hydrogen here, and then we have the 5-membered ring. So, is C1 here is a stereogenic center. So, when we look at the ring, we can see that actually this, the left and the right hand side is an identical groups. Okay, we can see is identical groups. So, no, C1 is not a stereogenic center. Okay, what about 3-methyl cyclohexene? Now we have methyl group, hydrogen group and double bond here. So, this double bond, because of the presence of the double bond here, is actually 2 different groups. Okay, this the left and the right hand side is a different group. So, yes, C3 is a stereogenic center because it is bonded to 4 different groups. In 3-methyl cyclohexene, the methyl and hydrogen substituents that are above and below the plane of the ring are drawn with wedges and dashes as usual. So, in order for you to determine the stereocenter, you have to draw the molecule in the 3D structure. Then you can see that it's actually bonded to 4 different groups. And then when you place this 3-methyl cyclohexene in front of a mirror, you will see that it's actually a pair of enantiomer because its mirror image is non-superimposable. What about other chirality center rather than carbon? Okay, so we have here silicon. Silicon, like carbon, can form 4 bonds in its stable compound, so it is also a chirality center here, the silicon. And then for nitrogen here, because its pyramidal geometry will produce a tetrahedral, it can become a chiral center. Okay, this nitrogen bonded to 3 other groups along with a pair of electron valence. So, example 1, locate the stereocenters in the following. Okay, for this compound, there are no stereocenter. Okay, because there is no carbon tetrahedral bonded to 4 different groups. In this structure, however, we have 1 stereocenter because this carbon is attached to 4 different groups: hydrogen, hydroxyl group, methyl group, and also this 1 group here. For this compound, we have a big compound here. We can identify the chirality center because there are 2 chirality center here. This carbon is attached to ethyl group here, bromine, hydrogen, and also this whole bunch of groups. Well, for this carbon also again similar. Okay, they are attached to ethyl group here, bromine, hydrogen, and also 1 whole bunch here. Even though there are stereocenter in this molecule, it does not mean that it is a chiral, because if you put this molecule in front of a mirror, you will see that actually this molecule is it has a superimposed mirror image. So this compound is actually a chiral. Okay, and then we have this structure. Here we can identify that there is 3 chirality center or stereocenter, because each of these 3 tetrahedral carbon is attached to 4 different groups. What about this one? A much longer molecule structure. From here, we actually can identify that there is 3 stereocenter. Why? Because each of these carbon is tetrahedral and is attached to 4 different groups. What about this compound? That is much more complicated. From all this compound, this carbon and other molecules such as nitrogen and silicon, you will see that there is actually only two stereocenter. Okay, these 2 are carbon atom or carbon chiral, because these carbon are tetrahedral and attached to 4 different groups, while this nitrogen are not tetrahedral. Okay, also this silicon is not tetrahedral. As a summary, a chiral carbon atom is the most common example of a chirality center. A chirality center belongs to an even broader group called stereocenter. A stereocenter or stereogenic atom is any atom at which the interchange of 2 groups give a stereoisomer. So this is the reference. If you have any question, feel free to email me at my email address, and thank you for listening.